In the previous lecture, we discussed and obtained some expressions for the different kinds of power gain that an MMIC amplifier can provide. Using those expressions were derived using the S parameters of the MMIC amplifier and also the source or the load impedances and different reflection coefficients as needed. So one thing to note is that something that we've been mentioning all this while so far is that whether it is the S parameters or whether it is the gain expressions that we are calculating using those S parameters, all of them are at a given frequency, because the S parameters of any device or circuit or this MMIC amplifier, so to speak, is a function of frequency. So therefore, let us write down those expressions for the gains that we had derived. There were essentially three power gains that we have derived. One was the power gain, the other was the available gain, and the last one was what is called as the transducer gain. So the power gain GP looks like this. So this is the power gain which we discussed was more load centric, because the load impedance essentially plays a very important role. Therefore, you have the gamma L terms and gamma in, which is the input reflection coefficient, or rather the input or the reflection coefficient that you see when you are looking into the input port of the amplifier, which is also a function of gamma L. So therefore, it is load centric. And as we said, this expression is often used for power amplifiers, where we need to feed a certain power to the load. So therefore, the choice of load impedance is quite important over there. The second one is available gain. GA, which was something like this. So GP and GA are essentially converses of each other. So whatever is the expression for GP, if you write it in the source centric terms, you will get GA. S22 gamma L will become S11 gamma S. The mod S21 square stays the same, and this gamma in will become now gamma out. So gamma out is the reflection coefficient we see when we are looking into the output port of the MMIC amplifier, and gamma out is a function of gamma S also. So just like how load impedance plays an important role in power gain, the source impedance plays a very important role in the available gain. So therefore, this is a source centric gain. And this kind of expressions are used for low noise amplifiers, where the input side is more important to design than the output. The third gain is what is called as the transducer gain, or GT. So the expression that we had derived or we had obtained was something like this. So here, as you can see, this depends on both source impedance as well as load impedance. So it sort of gives priority to both. So therefore, for general purpose RF amplifiers, where we need to consider both the source and load impedances, we need to consider the transducer gain. So therefore, this is a generic expression. right? So this expression, there is one more, it can be written in another way also. The same GT in this form can also be written in another way, which is a slight modification of this, that is 1 minus mod gamma s whole square. If you simply substitute the value of gamma in, you will get something like this. So just like how it was gamma in gamma s, here it becomes gamma out gamma L. So you can use either of these expressions, doesn't really matter too much. What is important to notice is that whichever expression you use for GT, it is still a function of both source and load impedances, or rather gamma S and gamma L. That is very important to know. With this backdrop in mind, let us now look at amplifiers in a little bit more detail. Normally for RF circuits and networks, as I said earlier, we judge them based on three criteria: whether they are matched, whether they are reciprocal, whether they are lossless. We know definitely that amplifiers are not lossless networks. They are indeed lossy. They are non-reciprocal, and they may or may not be matched. That is usually decided by what is the gamma values, gamma in, gamma out, gamma s, gamma L. That is up to the designer. So amplifiers are those kind of circuits where you can say that in general you cannot expect all those three criteria to be satisfied. Having said that, there are some issues which we need to consider for amplifiers in particular, which we don't consider for other RF circuits that we have discussed so far. And we are going to talk about those considerations. Why? Because amplifiers are active circuits. They have the potential to take some input and provide an output whose magnitude is larger than the input. So, therefore, what is happening now is that while we are claiming on one hand that the amplifiers in general are lossy, they also have the potential to amplify the small signal power or the voltage. That is like saying they have the potential to give increased output for an input of some magnitude, or magnitude is lower than that of the output. So it is important for us to know that the amplifier will do so very faithfully. That's like saying every controlled input or every input with a controlled magnitude will also give an output with a limited magnitude, or the term that we usually use is called as a bounded input, bounded output. So therefore, when I'm talking of bounded input and bounded output, the question of stability arises. Whether the amplifier can get into some trouble or get us into some trouble and give some voltage output which is much more than its input. Now, when I say output, I don't always mean at port 2. It could also happen that if the input is coming at port 1, the reflected voltage at the same port could be more than that of the input voltage. Well, usually that's not possible because we know that the magnitude of the reflection coefficient is usually below 1. But then again, those definitions were for passive circuits, where there is no possibility of having anything, any gamma whose magnitude could be more than 1. So let us look at this in some detail. Suppose I have this amplifier, MMIC amplifier. Again, let us consider frequency as some F0. It is fed with a source that has source impedance of some Zs, and its output has a load impedance that is ZL. This is port 1, this is port 2. Now let us say that the characteristic impedance of each of these lines is Z0. We will define, as we have done in the past, that the reflection coefficient looking into the input of the amplifier is what is gamma in. The reflection coefficient looking at the output side of the amplifier is gamma out. The reflection coefficient looking at the load is gamma L. The reflection coefficient looking at the source impedance is gamma S. So very quickly, I'll repeat what all these are. Gamma S is Zs minus Z0 divided by Zs plus Z0. Gamma in is the input impedance of the amplifier, Zin minus Z0 divided by Zin plus Z0. Gamma out depends on the output impedance of the amplifier, Zout minus Z0 divided by Zout plus Z0, and the load reflection coefficient gamma L, as we all know from before, it is ZL minus Z0 divided by ZL plus Z0. Now, what is little easier to handle is the source and the load. This is the source and this is the load. Usually what happens is that most sources and loads are faithful in nature. That is, we know that the real part of the source and load impedances are always positive. That means they have resistive components also, which can dissipate power. So therefore that's fine. So we'll say the real parts of Zs and Zl are positive. This is always the case. Usually we cannot have negative resistances so easily. So because of this, if you substitute them over here in these expressions, you can always prove that the mod of gamma S and the mod of gamma L will always be less than 1. And that's quite fine also. This is what we want. But what about the gamma in and gamma out? Gamma in and gamma out depend on the Zin and Zout of the amplifier respectively. Now remember, at different frequencies, at different bias conditions, the amplifier exhibits different properties. It exhibits different S parameters. So, the calculation of gamma in and gamma out are now to be done with some thought. Or we cannot say with 100% surety that the magnitudes of gamma in and gamma out would be less than 1. Because we cannot say what would be the value of Zin and Zout. Inside, there are not just R and C's, the resistors and capacitors, but there is also the transistor, which is made of semiconductors. And for certain bias conditions, the transistor may even exhibit negative resistance. It's rare, but it's possible. So therefore, while the source and load are usually manufactured in such a way that they have some resistive components, some positive resistance components, the real part of Z in and Z out are unknown, or rather they depend on bias. They can have positive resistance, they can even have negative resistance. Now, in case they have negative resistance, what's going to happen? The magnitude of gamma in and gamma out now will start getting more than 1. So whatever power I am sending over here, more power is coming back. And that is something that we don't want. Negative resistance immediately means that the device or the amplifier circuit may have the ability to generate waves of its own, and that is called as oscillations. If it resonates properly, it might generate a wave of some other frequency also. That frequency is unknown, but it may generate, and that is an example of something that is an unstable circuit. So we'll say if the real part of Z in and Z out is more than 0, then gamma in and gamma out magnitudes are below 1. But if this quantity is now less than 0, then the gamma in and gamma out would be more than 1 in magnitude. This is called as stable, and this is unstable. That is what we are looking for. So therefore, gamma S and gamma L we can find out easily, but gamma in and gamma out we need to be little careful. So therefore, if you want the amplifier to be stable, the reflection coefficients looking into the input stage and the output stage of the amplifier, or in the input side or the output side of the amplifiers, should be less than 1 in magnitude. This is what we want. This is what we don't want. So therefore, I'll put a danger sign. This is something we don't want. Now, let us see how we can obtain this. Let us see how we can obtain this. First things first, we will look at the MMIC chip that we have. We look at the MMIC chip that we have. So let us say this is my amplifier. This is my amplifier. Suppose this is port 1, this is port 2. This is the input port and this is the output port. We expect that any input at port 1 should get amplified and come out at port 2. So therefore we know that the mod of S21 or the voltage gain should be more than 1 usually, because S21 corresponds to the voltage gain. Although not fully, but this is the intrinsic voltage gain. What about S12? S12 is input at port 2 and output at port 1. Now that is a very strange case where we know that an amplifier is a non-reciprocal device. We give the voltage at the input terminal, the output port will show us usually a more magnitude output. So therefore, if we give some input at port 2, we don't expect to see anything at port 1. So usually what happens is that S12 tends to 0. So if we are giving an input at port 2, we expect the very negligible amount of that signal to come to port 1. So therefore, in most MMIC amplifiers, this is valid. There are some cases where the amplifier is not designed properly and the S12 can be something finite, much more than 0. But for most cases, S12 tends to 0. And such kind of amplifiers are called as unilateral amplifiers. Unilateral means it can pass only from port 1 to port 2, but not from port 2 to port 1. Okay. So suppose we look at the transducer gain, GT, that is 1 minus mod gamma S. I have not shown the source and the load, but we'll just assume that they are there. So now, in this general case, of in this general case of the transducer gain expression, let us put this condition of unilaterality, that S12 tends to 0. So where is the S12 term over here? We cannot see it, but S12 actually influences gamma in. So if gamma in, as we have derived the expression earlier, is S11 plus S12 S21 gamma L divided by 1 minus S22 gamma L. So if S12 tends to 0, this term will vanish. So this entire second term will vanish and gamma in will be equal to S11. So if we now put this over here, so we will call this as something called as GTU, that is transducer gain in the unilateral case. That would be nothing but now gamma in will become S11. So therefore this will be 1 minus mod of gamma S square divided by mod of 1 minus S11 gamma S whole square times S21 square times 1 minus mod gamma L square divided by mod 1 minus S22 gamma L whole square. Now you can see the source side terms and the load side terms are kind of equivalent or symmetric. So this expression has now become quite symmetric. So this is what the gain looks like now. But when we say that the S12 is 0, what about the gamma in and gamma out? Gamma in, we said, reduces to S11. Now what about gamma out? Gamma out is just the opposite expression for gamma in, S22 plus S12 S21 gamma S divided by 1 minus S11 gamma S. So if S12 becomes 0, this term also vanishes and gamma out becomes S22. So therefore, if the MMIC is unilateral, that means its S12 in magnitude is almost 0, we can say that the way to have gamma in and gamma out less than 1 in magnitude will only happen if the S11 and S22 are themselves below 1 in magnitude. So in this case, we will say that for unilateral amplifiers, these are what we need. So what happens? Gamma in, S11 magnitude is less than 1, and here S22 magnitude is less than 1. Why? Because gamma in is equal to S11 and gamma out is equal to S22. So These two conditions are needed to ensure stability from the input side as well as the output side. Now what happens is that since gamma in usually depends on the load and the gamma out usually depends on the source, this criteria is called as the output stability criteria. And this is called as the input stability criteria. So therefore, we can say that for unilateral amplifiers, so long as the mod of the S11 and the mod of the S22 are below 1, the amplifier will be always stable. Now what do I mean by always stable? Whatever be the source, whatever be the load, they will always be stable. You see, an amplifier will be unstable under certain conditions. I said that when the Zin or the Zout may have some negative resistance components in them, they may become unstable or they may start to oscillate. In such cases, what happens is that the choice of the source and load impedance also becomes important. The way I'm choosing the source or the load impedance, they may either support those oscillations, they may also hinder those oscillations. Obviously, we would want them to hinder the oscillations, but then that is not guaranteed. So therefore, for cases where the amplifier could become unstable, the choice of source and load is very, very important. But what we are seeing is in the case of unilateral amplifiers, so long as the mod of S11 is less than 1 and the mod of S22 is less than 1, the amplifier will be stable no matter what is the source, what is the load. So therefore, this is called as, we'll write it in the form of a statement, as long as the mod of S11 and the mod of S22, they are both below 1, the MMIC unilateral amplifier is what is called as unconditionally stable. Means irrespective of ZS and ZL. Irrespective of ZS and ZL. Right? So this is one thing called as a test for stability. If they are, one of them is more than 1, then we need to be careful. Now, having discussed this so far, let us now go to a more difficult case. When the amplifier is non-unilateral. That is the case when the S12 is not 0. It is something more than 0, much more than 0 in fact. Obviously, the criteria are still valid that we need gamma in less than 1, we also need gamma out less than 1 for stability. So, therefore now, the expression for gamma in and gamma out are no longer as simple as S11 or S22 respectively. They are something much bigger. So the analysis becomes little tricky. The question now is that is there any way through which we can very quickly find out whether the transistor has stable characteristics or unstable characteristics. And the next question is, in case if it is probably not stable, it may exhibit some unstable characteristics. Just like the case of unilateral amplifiers, can we do something to make it stable? Can we do something to make it stable? So what happened? So let's write these two questions. The first question is, can we do something to identify whether the amplifier is unconditionally stable? If the amplifier does not satisfy this test, so if an amplifier is not unconditionally stable, then what is it? We call it as potentially unstable. What it means is that under some cases it may become unstable, under some cases it may still remain stable. So we'll call it as potentially unstable. Then what can be done to keep it stable? These are the two questions we need to answer. Well, let's answer the first question because it's easier. After a lot of analysis, there's a lot of mathematics that's involved, and many of that mathematics is beyond the scope of this course. So what scientists have done over the past few decades is that they've come up with ways which are called as stability tests or quick tests for stability, especially in case of non-unilateral amplifiers. So let's look at the first test. I will not derive these tests, they are just given to you. You can take them the way it is and apply them without having any doubts. The first test is named as a K delta test. Where we define two quantities. The first is the delta. This delta is nothing but the determinant of the S matrix. So if the S matrix is this S11, S12, S21, S22, then the delta is S11, S22 minus S21, S1. Using this delta, you can calculate another quantity called as K, and that is defined in this manner: 1 minus mod S11 square minus mod S22 square plus mod of delta square divided by 2 times of mod S12 S21. So this test says that once you have calculated these quantities K and delta, the K will always be real. Because it is making use of magnitudes. So it says if K is greater than 1 and the mod of the determinant delta is less than 1, then the amplifier is unconditionally stable. Means whatever be the source impedance, whatever be the load impedance, the amplifier will always exhibit stability. If not, then it is potentially unstable. So this is a very quick test to find out. The second test is test number 2, which is called as the KB test, which is not very important, but it was derived as an extension of the K delta test. So the K is the same as before, which we have calculated. They defined one more quantity called as B, which is also a real quantity. This is nothing but 1 plus mod of S11 square minus mod of S22 square minus mod of delta square. So they say if K is more than 1 and this B is positive, again this is a real quantity. If K is 1 and B is positive or more than 0, then the amplifier is unconditionally stable. Else, it is potentially unstable. So tomorrow, if you are given any amplifier, if you are given any MMIC amplifier and you are asked to check whether the amplifier is unconditionally stable or potentially unstable, you will immediately go to the frequency that you desire and you will look at the S parameters of the MMIC at that frequency, and then you can do these tests. Either any of the tests is fine, test 1 or test 2. Usually we go for test 1 most of the time because it's a lot simpler. You don't have to calculate this additional quantity. So if you do those tests and the amplifier passes that test, you say that it is unconditionally stable. You can freely go ahead and use whatever source or load impedance that you want. Of course, these tests are valid for non-unilateral devices. Why? Because over there, these quantities depend on S12 also. If the device is unilateral, that is when S12 is very, very small, then the problem becomes much more simple. All you need to do is take a look at the S11 and S22 of the MMIC at that frequency, and if they are below 1 in magnitude, you say that it's unconditionally stable. So you can freely go ahead and use whatever source or load impedance that you want without having to worry about anything. So by discussing these two tests, we answered the first of the two questions. Is there any quick way to test whether the amplifier is unconditionally stable? Now, it is time for us to see the second question. That is, if somehow we see that the amplifier is unconditionally not stable or it does not pass the stability test. That means if it is potentially unstable, then what can we do to ensure that it is stable? Now it is time to answer question number 2. Well, let us look at the general case first, in case of non-unilateral devices. So let's define the output stability criteria and then the input stability criteria. So output stability means we want that the mod of gamma in should be less than 1, and for the input stability criteria, we want the mod of gamma out should be less than 1. These are needed. So, over here, what is gamma in? Let's write the formula. This should be less than 1. And for the input stability, so what we are effectively seeing is that this gamma in and gamma out are functions of multiple quantities. But the good part is that these S parameters which I am taking, they are all fixed. This gamma L over here and the gamma S are variable. That's like saying, for an MMIC that is given to us, its S parameters are known to us, they are decided and measured by the manufacturer, and they are known to us. They are known to us. So, we cannot do anything about that. We cannot say that, okay, take a hammer, break open the chip and do some hocus pocus to change the S parameters. No, that is not practical. What we are seeing is that if we need the MMIC to be stable, we need that the gamma in magnitude and gamma out magnitude should be less than 1. And to do that, we need to check something that is in our control, and that is gamma L and gamma S. In other words, the source impedance and the load impedance. They are outside the amplifier. They are outside the amplifier. And then we can say that by judiciously choosing the ZS and the ZL and thereby influencing the gamma S and the gamma L respectively, we can do something to make this gamma in stay below 1 or gamma out stay below 1 in case somehow they try to go out of bounds. But the amplifier can be potentially unstable when it fails one of these two tests, or if the S11 or S22 in magnitude they become more than 1. Of course, both are needed. So, when this happens, we can also say that even without doing the stability test, we can say that yes, they may be potentially unstable. So, therefore, it is important for us to see what we can do using the gamma S and the gamma L to make the gamma in and the gamma out stay below 1 in magnitude. So therefore, if I say the borderline stability, So for the, let us say, the output side, and here we have the input side. Output side we need mod gamma in should be less than 1, and for the input side we need mod gamma out should be less than 1. But for borderline stability, what we will say is that they should not be less than 1, they should be equal to 1. This is what is called as borderline stability. So now let us substitute the formula for gamma in and gamma out. And over here it will be right. So then you can do something, you can do some manipulations and try to isolate gamma L over here and gamma S over here as a variable, or separate it from the rest of the terms and try to do something. So what we see is if you solve these two expressions, one over here and one over here, you will end up with something like this. The derivation is a little long, so don't stress out too much about it. Sorry, it will be gamma L. We're talking of gamma L, so it will be gamma L minus S22 minus delta. Now this delta is the determinant of the S matrix at that frequency as we spoke about. Delta times S11 conjugate, the whole conjugate, divided by mod S22 square minus mod delta square whole mod is equal to now S12 S21 divided by mod S22 square minus mod delta square the whole mod. This is what you get. And for this you will get something very similar or equivalent, that is gamma S minus S11 minus delta S22 conjugate the whole conjugate divided by mod S11 square minus delta square the whole mod is equal to mod of S12 S21 divided by mod of S11 square minus delta square mod the whole mod. These are the two expressions that you will get. The derivation once again is not important. By doing the complex analysis for these two equations, this is what you will end up with. This is what you will end up with. So what we see, if we were to look at these in a more close format, I can say that this looks something like the following. Mod of gamma L minus some complex quantity. The denominator is real, but the numerator is complex. So let's call this as some CL equals a real quantity. So let's call it as R suffix L. Over here what I am seeing, mod gamma S minus, again a complex quantity, let's call it as some CS equals a real quantity, we'll call it as RS. So if gamma L and gamma S are variables, if gamma S and gamma L are variables, we see that the other quantities CL and RL over here and CS and RS over here, they are fixed. Why? Because CL and CS, RS, RL and RS, they depend purely on the S parameters. So this is constant, this is constant, this is constant, this is constant. These two are variables. So if you were to draw the trajectory of these two equations on the complex plane, you will essentially see that these are circles. These are essentially circles which have a lot of significance. and what the significance is, we shall discuss this in the next lecture. So in today's lecture, we started with the discussion on stability. We looked at what is a unilateral amplifier, a non-unilateral amplifier. We looked at the criteria for stability for both unilateral and non-unilateral amplifiers. And we saw some tests for stability, and we saw that if the amplifier passes those tests, it is unconditionally stable irrespective of the source and the load impedance. But if it does not pass the test, it is potentially unstable. And if so, we started or embarked on a process to see if the amplifier is potentially unstable, then what can be done to judiciously choose the source and load in such a way, or the gamma L and gamma S in such a way, so as to keep the amplifier stable for most of the operation. We shall continue, as I said, in the next lecture. Thank you.